Before we do the next example, let's review the intermediate value theorem. If you have a function that's continuous on a closed interval of x values from a to b, and there's some real number n that's wedged between the y partners of these endpoints, f of a is the y partner to x equals a, and f of b is the y partner to x equals b. So you got this, a real number n wedged between those two y values. And if you know that those two y values are not equal to each other, f of a is not equal to f of b, then you can be sure by the intermediate value theorem that there exists some x value c that's on the open interval from a to b. It's some number in the open interval from a to b, such that it has the property that when you evaluate f at this c, you're going to get the n that you discussed in this supposition above. All right, now let's go to our example. Over here, we're asked to use the intermediate value theorem to prove that the cube root of x equals 1 minus x has a solution between x equals 0 and x equals 1. What does it mean to say that this guy has a solution? Here's our proof. A solution of this expression, this cube root of x equals 1 minus x. Well, that's the same as asking for a solution of the equation cube root of x plus x minus 1 equals 0. In other words, you can move everything to the left side and have the right side be 0. But that is the same as asking for the root of the f of x equals the cube root of x plus x minus 1. So that's the way we're going to view this problem. We're looking for the root of this function. Now, I just want to remind you what it means to be a root. To be a root of a function means that you're the x value for which the y partner is equal to 0. So keep that in mind. All right, let's use the intermediate value theorem with this f of x equals the cube root of x plus x minus 1. And let's use the closed interval of x values from a to b to be equal to the closed interval from x equals 0 to 1, and let's choose our n value that we want wedged in the middle to be equal to 0. And that's because we're looking for the existence of a root, x equals c, such that f of c is equal to 0. That's what it means for c to be a root. That's why we're choosing n to be equal to 0. Step 1, we're going to show that the function f is continuous on the closed interval from 0 to 1, where f of 0 is not equal to f of 1. Well, just think back about root functions. Here we have the cube root of x. Root function cube root of x we know is going to be continuous on its domain from negative infinity to positive infinity. Well, we're only interested in continuity on the interval from 0 to 1, and that interval is contained in the interval from negative infinity to infinity. Therefore, our root function cube root of x is continuous from 0 to 1. Polynomials are continuous on their domain, all real numbers, so our interval from 0 to 1, on that interval we have continuity of the polynomial x minus 1. Therefore, their sum, f of x equals cube root of x plus x minus 1, will be continuous on the same interval from 0 to 1. So we broke it down into pieces, put them together, and showed that their sum is going to be continuous. Step 2, let's show that the y partners, f of a is smaller than our n value 0 is smaller than f of b. In other words, f of 0 is less than 0, that's our n, is less than f of 1. Well, what's f of 0? It's a cube root of 0 plus 0 minus 1. Just evaluate it. What do you get? You get cube root of 0 plus 0 minus 1 equals negative 1. Well, that's certainly less than n, which is 0, and that's less than 1. Where did 1 come from? Well, 1 is what you get when you evaluate f at x equals 1. It's a cube root of 1 plus 1 minus 1. That's equal to 1. So here we see that negative 1 is less than 0 is less than 1. So we meet the second condition. So we're now allowed to do step 3. We're allowed to apply the intermediate value theorem since all the conditions were met. Thus, by the intermediate value theorem, there exists some value x equals c on the open interval from 0 to 1 such that f of this c is equal to 0. Now, what does that mean? That means that the cube root of x equals 1 minus x has a root x equals c between 0 and 1. So we're finished.